Question 6 has four parts, parts A, B, C, and D, and these are a little bit more involved solving equations. I think probably the most straightforward one is D, but that does involve a distributed property and getting rid of 2x squareds from each side. But let's start with A. So if you recall, quite a while ago we had talked about this method of looking inside, and we're going to deploy that at some point. But I want you to consider this. So I'm going to put a rainbow box here, and I just want to say that I'll write something similar here. So here's another box. I've got 2 times some magical box plus 6 equals 24. So I'm choosing to think about this. The square root of 3x plus 6 is kind of it's not really a super variable, but it's something that I want to isolate first. And in isolating that, I'm just going to subtract 6 from each side of this equation, and that will give me 2 times this box is 18, and then I'm going to divide by 9. So the box is 9. So what I'm saying here is this box, right, has to produce a value of 9. And the other thing is I know is I'm taking the square root of the stuff that's inside of the box. So this stuff inside the box has to be 9 squared. It has to be the number 81, because it is precisely the square root of 81 that would produce the value of 9 that I need. So I'm going to just write this equation. I'm going to say, look, this 3x plus 6 must be the number 81. And if it is, then this entire thing on the left-hand side should equal 24. So again, I'm going to subtract 6 from both sides. 81 minus 6 does give me 75. So I have that 3x is 75. Again, I subtracted 6 from each side. And when I divide by 3, I get that x has to be the number 25. So x, this variable, must be the number 25. So that's my solution. Now, to verify that, I just need to know that when I plug 25 in to that equation, it does indeed produce an output of 24. So I might show that by doing this. I might say 2 times the square root of 3 times 25 plus 6, and then plus a 6 outside of the radical, and I'm just checking to see, and sometimes I'll just draw a line down the middle. I'm checking to see that that is the number 24. It's an open question. This is 75, and 75 plus 6 is 81. So I have here 2 times the square root of 81 plus 6, and you guessed it, 2 times 9 plus 6, and this is 18 plus 6, and 18 plus 6 is indeed the number 24. So this value, x is 25, right, produced 24 on both the left and right hand side of this equation. So it is indeed the solution. So let's take a look at B. B is an equation where we're going to use fraction busters. And what I'm going to choose to multiply both sides by first is 3 times x. 3 times x. Now, think about the big picture, right? I have an equality, and because this is an equation, what I know is that I'm free to multiply all the terms on both the left-hand side and the right-hand side by the same value, and I won't change the nature of this equality statement, right? This equality will be preserved. So I'm choosing to multiply both sides by 3x precisely because I know it will destroy both of the fractions that I see here. And in fact, let's go ahead and multiply this. There's 2 terms on the left-hand side, and when I multiply the 3x times this first term, which is 1 over 3x, it produces exactly 1. And then when I multiply 3x times 5, it produces 15x. So already I like how this looks. It looks a lot better than the original equation. Then over on the right-hand side, I do have a common factor. You can see if you look, it's a giant 1. There's an x over an x. So I can eliminate that giant 1, and the only thing I'm left with is 2 times 3, or 6. So it equals 6 on this side. And then of course I can take away 1 from both sides. That will give me 15x is 5. And I can divide both sides by 15. And that would be x is 5/15. And 5/15 of course is the number 1/3. So 1/3 is the solution. X is the number 1/3. Now, in terms of checking that, right, I need to plug this into that original equation. So let me go over here to the side where it says check. So I'm going to write a 1, and then in my denominator, 3 times x. Well, x is 1/3. So I've got 3 times 1/3 in that denominator, and then plus the number 5. So let's simplify that. 3 times 1/3 is 1. So I've got 1 over 1 plus 5, which is simply 1 plus 5, or 6. So the left-hand side is the number 6. Over on the right-hand side, it was a 2 divided by x. But we know that x is this fraction 1/3. So a couple ways I can deal with that, right? I can just, you've probably seen this. This is equivalent to 2 times 3 over 1. But if you've ever wondered why that is, we know that 1/3 can be written as 3 to the negative 1 power. Okay, so this is equivalent to what I've written below, right? 2 over 1/3 is the same thing as 3 to the negative 1 power. And if I want to get rid of this negative exponent, I can multiply 3 to the first in both the numerator and denominator. The idea here is that I'm free to multiply anything by the number 1 and not change its value. So when I multiply 3 to the first over 3 to the first, I'm not changing the nature of 2 divided by 3 to the negative first. However, I am changing how it looks, because 3 to the negative first power times 3 to the first power is exactly the number 3 to the 0, which is the number 1. And in my numerator, I've got 2 times 3, which is the number 6. So 2 different ways we've seen this here. We do get 6 on each side when x is 1/3. So that's our solution for B. X has to be 1/3. Let's take a look at C. On C, I can see that I've got 1/3 and 1/9. And because I'm seeing the 3 and the 9, I might choose to think about powers of 3. So, for example, 3 to the first, 3 to the second, 3 to the third. I know that 3 to the first is 3, 3 to the second is the number 9, 3 to the third is 27. If I go backwards a little bit, 3 to the 0 power would give me the number 1. 3 to the negative first power is this fraction 1/3. 3 to the negative second is this fraction 1/9. Now, the two values that I'm interested in here are the fact that 1/3 can be written as 3 to the negative 1. That's going to be helpful here. And the other thing that I have is the fact that this 3 squared is the number 9. So that's going to be helpful with rewriting this portion of the equation. So what I'm doing is I'm going to switch this so my base is the number 3 on both the left and the right hand side. So it looks like this. 1/3 again is 3 to the negative first power, and then I'm just raising that to the 3x plus 1. So again, all I've done is I've replaced 1/3 with 3 to the negative 1, and I can do that because they are totally the same. They're equivalent to each other. On the other side, I'm going to write 9 as 3 squared, and that's totally okay too, because 9 is 3 squared, but I need to raise that to the 4x power. The last thing I'm going to do is I'm going to apply the rule power to a power. If you'll recall, if I have a power, like for example, if I have a to the b, and that's getting raised to the c power, the shortcut for that is that's a to the b times c power. So I'm just multiplying the original exponent times the exponent outside. A little bit of care is required here, because I am going to have to multiply this negative 1 by both the 3x and the 1. And when I do that, this will become 3 to the negative 3x minus 1. And on the other side, that's going to be 3 to the 8 and then x. Now, this is exactly where we want this to be. I now have identical bases. Both the left and the right hand side have just the base of 3. And the only way that this equality can be true, the only way this can be true is if the exponents are actually equal to each other. So we just force the issue and we say, look, this exponent must be the same as the other exponent. So we're just going to see the value of x that makes them truly equal to each other. And of course, if I add 3x to both sides, I would get -1 is 11x. And then I could divide both sides by 11, and I would get -1 over 11 is precisely what x is. So x is -1/11. I'll write this here, -1 over the number 11. Okay, so time to check this one, and I have to say this is probably it's probably a fairly difficult expression to check. So I'm going to choose to use my calculator. I'm going to plug in this -1/11 and just verify that both the left and the right hand side are the same. So to do that, let's go ahead and enter that fraction first. So we'll turn on our calculator and we'll go ahead and I don't need this. Whoops. And I don't need this at all. I'm just going to hit alpha and F1 to grab the fraction template. And when I'm looking at this, I'm just going to place a -1 in the numerator, and I'm going to place 11 in my denominator. So I've got here the fraction -1/11, and I'm just going to verify that that produces the same thing on both sides. So let's start with the left-hand side. I'm going to need another fraction template, so let me grab it. This is, and this fraction is a 1 over 3, and I'm going to raise that to the power of, and I guess I'll use some parentheses here. I'm going to go 3 times, now I need to go get that fraction, so here it is. So 3 times -1/11, and then plus the number 1, and close the parentheses, and I'm just going to press equal. So on the left hand side, when x is -1/11, I get 44.79. Okay, so what about the other side? It looks a little bit more, it's more simple to deal with, so I'm just going to enter a 9 and raise that to the power of 4 times, let me go grab the fraction, there we go. So that's 9 raised to the power of 4 times -11 first. And when I press enter, it gives me again 0.44978. So here's what I'm going to include for my check. I'm just going to say when x is -1/11, both the left hand side and right hand side equal 0.44978, etc. So, and that's really what we're looking for, right? We're looking for a value of x that makes this equality statement true, and when x is -1/11, both the left hand side and the right hand side are genuinely equal to each other. Our final equation is 2x times the quantity of x plus 5 plus 3, and on the other side we've got 2x squared plus 9x plus 10. So I'm just going to apply the distributive property here. This is pretty straightforward because it is just a monomial times a binomial, so each one of these are going to get multiplied by 2x. So 2x times x is 2x squared, and 2x times 5 is 10x. Don't forget that I have a 3, and then over here I've got the 2x squared plus 9x and then plus 10. So both sides have a 2x squared, so I'm going to subtract that from both the left hand side and the right hand side, and I'm left with 10x plus 3 is the same thing as 9x plus the number 10. If I subtract 9x from each side, right, this gives me now that x plus 3 is 10, and I can now subtract 7 from each side, and that would give me that subtract 3 from both sides. I'm getting ahead of myself. 10 minus 3 is 7. So I believe x is 7, and I'll write that down. I think x is the number 7. And then to verify that that really is the case, I'm going to go ahead and plug that value in. So I think I'll just do this manually. This is going to be a 2 times a 7, and then I have to multiply it by the quantity of 7 plus 5, and then I add a 3. And then on the other side of this, we're going to take 2 times 7 squared. I'm going to add 9 times 7 and then plus 10. So 2 times 7 is the number 14, and I'm going to multiply that by 12 and then add the number 3. 14 times 12 is 171, and when I add 3 to the, no, it's not 171. What is 14 times, I'm sorry, I'm embarrassed to say I'm going to do this anyways. 14 times 12 is 168. Yeah, I did it again. So this is 168, and then I'm adding 3 to that, 168, 169, 170. So this is 171. So when x is 7, I produce a value of 171 on the left-hand side. On the right-hand side, this is 2 times 49. 9 times 7 is 63, and then don't forget the plus 10. 2 times 49 would be 98, plus this would be 73. And if I combine 98 and 73, 8, 9, 10, 11, carry the 1. Yeah, it is. This is also 171. So when x is 7, both the left-hand side and the right-hand side become the number 171. So this is the verified solution to this equation. X does equal 7.